Okay, we're in the section on improper integrals. This is section 11 of the notes. And I'll go through the lecture material first, which is typical of the course, lecture first. It'll be a short lecture. Basically, it's me outlining what's indicated in the notes over here. This is something for you to study and try to comprehend before you do the examples. So it's going to be introduced first. We'll go through, I think it's about 3 pages of notes. And then we're going to do examples later. All right. So that's typical format course, little tiny lecture. Then we try to reinforce what we've presented in the lecture by doing examples. And then there'll be a chance in the homework for you to try on your own. All right. So I'm going to go to the whiteboard and we're going to talk through the notes. All right. So just give me 1 second to do so. Okay, we're on the whiteboard. So let's talk about improper integrals. And they have types. Not that these types are, let's say, oh, this is type 1, that's type 2. Whoops. So what I'm going to do over here is just simply talk about the form of the integrations we're going to be given. These are going to be definite integrals. There's going to have limits on it. So what I mean by that, you're going to see an integral like this over here. We're going to say that this integral exists for all b greater than a. Now, what I mean by that is that these are finite numbers now, all right? So for some finite number b, some finite a, such as b is greater than a, well, then they go on to say, then if we have this one over here, now clearly infinity is greater than a, what we need to do is we need to rewrite the integral as a limit problem, all right? And the limit is going to be now the b is going towards infinity. Here's the deal though, what we're going to do is we're going to try to integrate this guy over here with those limits. After we do the integration, finding antiderivative, plug in the substitute the values in for a and b, what we're going to do is take the limit. All right. So what does it say then? It goes on to say, provided that this limit exists. So that's going to be the end of our problem. Does the limit exist? All right. If the limit exists, we're going to say it's convergent. If the limit doesn't exist, we're going to say it's divergent. All right. So there's also a similar case here. And again, really, it's really the same thing. B and a are the limits of the integration where b is greater than a. All right. And now we're going towards minus infinity. All right. So what do we do? Rewrite the integral. I'm just going to simply say a now, but a is going towards minus infinity now. What does it say? Provide the limit exists. We provide that exists. All right. If it exists, we're going to say convergent. If it doesn't exist, we're going to say divergent. And certainly we'll take examples. All right. This one over here, we have, we're going in both directions. We have to split it. And what we do is we pick some arbitrary number between minus infinity and infinity. Let me just say a, where a is between minus infinity to infinity, and split into 2 different integrations. All right. So if you see this over here, we're going to split it at a and put down 2 different integrations and then do the limits for those separately. All right. So it says, split the integral into 2 parts, selecting a to be any number in the real number line. Typically we take 0, but again, you can be creative, take your phone number if you like. It's certainly between minus infinity to infinity. And then we're going to do both the right and left integrations. What do I mean? Going towards minus infinity, going toward positive infinity. Let's take an example over here. And this is where a lot of students struggle. They say, what do you want me to do? We need to know this improper. So the first thing we want to do is we want to write it as a limit problem. This is going to be limit. And let me write the integration down. I'm going to say 0 to a, and a is going towards infinity. And what do you get over here? X, e to the minus x, dx. Now, what I want to do on the side is I want to do the actual, the indefinite integral, because this might get really kind of cumbersome, have to keep writing the limit down again and again. And I'm going to say this one over here, probably you're going to be using integration by parts. Let's try that. I'm going to say u is equal to x. And now it means e minus x dx equals dv. You know what? In the past, I did that a little differently. So let me write that down maybe a little differently. I'll get my eraser out. I think I normally write down dv first. dv is equal to e to the minus x dx. du is equal to dx. V would be minus e to the minus x. Well, I'm going to take this, and this is, again, this is side work now. This is my side work. I'm just seeing if I can do the integration, right? So what do you get over here? Equals, what's going to be minus x, e to the minus x, minus the integration. Well, now it's minus a minus, so plus e to the minus x dx. And I can certainly do that. What do you get over here? Minus x, e to the minus x, minus e to the minus x, plus some constant integration. So I know I can do the integration. Now what I'm going to do, I'm going to write down. So what do I write down? Limit as a goes to infinity. Again, I want to remind you, it's minus x, e to the minus x, minus e to the minus x, limits of integration 0 to a. I'm going to write this down, making a substitution. It's going to be limit as a goes to infinity. Upper limit is going to be minus a over e to the a minus 1 over e to the a minus, well, lower limit now, right? So it's going to be 0, right? So what do you get over there? Well, it's going to be, 0 times, so I'll write it down, 0 over e to the 0. And then it's going to be, well, that's a minus, right? Minus 1 over e to the 0. All right, let's be careful about this. I'm looking at these limits over here. Clearly 0, clearly 0. And what he left off with, some arithmetic to perform, right? And what do you get over there? Plus 1. This is convergent. Let's go to the next page. And that work is put in the blue area over here. And, certainly I did this thing with the value of the limits on it. Then I took the limit. It looks a little different, but it's really the same problem. All right, same thing. All right, so improper integrals type 2. Let's take a look at it. And, just doing this is trying to understand what you're reading here. And it says, and I'll read it to you. It says f is continuous on an interval. This is going to be, it's going to be open at B, closed at A. So f is continuous on this interval over here. All right. And it's discontinuous at B. All right. So we all take examples of that. And what I'm saying is something happens at B. All right. So what do they want you to do? They really want you to rewrite the problem as a limit problem. But as I do this over here, I want to point out, you have to be really sensitive about the interval. And I'll put the interval down for you. The interval starts at A and it stops at B. The understanding is we're looking at this part of the problem. So there's only one way I could approach the B. And the only way I could approach this B, which is my troublesome number, is from the left side. Right? This is why we have this written over here, that we're going to approach B from the left side. All right. So I'll write that down as a limit problem now. All right. Now we're going to go on to say if the limit exists. If the limit exists, we're going to say convergent. If the limit doesn't exist, we're going to say divergent. All right. Let's keep going. This one's a little different. And let me point out to you what you're getting over here. You're getting another interval. Let me put that interval looks like to me. Whoops. This looks like A, B, and everything in between. Well, A is our troublesome number. And how are we approaching A? Well, it's got to be from this side, which is the right side. Let me point that out to you. We're going to write that down, right side. All right, so we just rewrite the integral. And again, we'll take examples of that. So we're looking to see if the limit exists. If it does exist, we're going to say convergent. If it doesn't exist, we're going to say divergent. All right. So if f has now is the discontinuity at C, again, we'll go through examples. What we need to do is, and certainly C is between A and B. And again, I got this over here, and there's a discontinuity at a number in between A and B. All right. So if f has a discontinuity at C, and that's between A and B, right? So what do we do? I'll put an interval down for you. And what are we saying? We have an A here, and we have a B over here, and there's C somewhere in the middle. And what we're doing is we're looking at, A to C, we're looking at this part here, and C to B, this part over here. So what are we doing? We're looking at the troublesome area. And the troublesome area again is at C. Well, we can easily take the integral and split it. And that's what we do. We split. Remember, C is our troublesome number. So what are we doing when we're from A to C? We have to do a limit. How do we approach C? And let me point this out to you. Over here, we approach C from the right side. Over here, we approach C. I'm sorry, I made a mistake there. On this one over here, we approach C from the left side. From this one over here, we approach C from the right side. All right, let's take a look at an example. And again, I'm looking at it, and you should have some impression about this problem over here, that there's trouble at the number 2. Let's write this down for you. All right, equals, I know there's problem at 2, so I'm going to say limit, right? I want to point out what I mean by this. We're looking at this thing 2 to 5. This thing is defined at 5, but at 2, we have division by 0. How are we approaching that 2? From the right side. So let's write this down. So we're going to approach the 2. I'm going to call that A. And what we're going to do, we're going to say, let's see what letter we want to use. I'll put this over here. 1 over, and it's going to be 5 here. And we want to approach 2 from the right side. All right. And it's going to be x minus 2 dx. All right. So the first step is just writing that integral down. All right. The next step is to actually do the integration. And let's write this down for you. I'm going to do this over here. I'm not saying you can't do this quickly. I'm not suggesting otherwise. I want to go through the steps. U would equal x minus 2. Du would equal dx. This is side work. Not everyone needs to do that, but some students do. What do you get over here? Well, 1 over u, root of u, I'm sorry. And then you're going to get du. Well, what is this going to give me? U to the minus 1/2 du. Well, that's pretty simple to do. What do you get over there? You get u to the half. Divide by half, like multiplying by 2 plus c. What's u? Well, I hope you remember. It's this thing, right? Look at over here, x minus 2, right? Plus c. All right, so I did that. Let's put this over here. And I'll write down for you. So it's going to be 2 root x minus 2 limit integration a to 5. Let's write this down. This is going to be limit. Whoops, I'm sorry about that. A goes to 2 from the right side. This would be 2. Well, 5 minus 2 is 3. That's not so bad. Minus 2 root a minus 2. All right, what do you get over here? Well, doing that limit, you're going to get 2 root 3. And this guy's limit over here, whoops, sorry about that. This guy's limit over here, if you're approaching 2 from the right, this is going to approach 0 from positive numbers. So this is fine. It's going to be 0. So this is my answer over here. So the integration turns out to be a kind of a nice number over here, and it's convergent, right? It converges to that number 2 root 3. All right, so I'm going to say that's done. Let's go to the next page. Let's see what their work looks like. And they're using T. I used A. It doesn't matter what letter you're using. Just don't use X, by the way. So I did this over here. Everything is done. All right, this one, when I say it gets a little bit tricky, the reason it gets tricky is, finding a comparison. And this is always tricky. You don't find a comparison it's easy. Like, can you compare someone to somebody? Like here, we're comparing integrands, all right? And again, this is going to be something that's going to require some thinking. And people get confused when they have to think, all right? It's not so straightforward, but this is going to be a comparison theorem. And certainly we'll go through examples. So it says, suppose f and g are continuous functions, or f is greater than g, and they're all positive. They're greater than or equal to 0. I should say non-negative. For x greater than a, for all x greater than a. Right. So visually speaking, what I'm seeing over here is, on some interval greater than a, and let me write that down for you. In some interval greater than a, I have two functions. One is f, and it's above the 0. So I'm going to say something like this. This is f of x. And g of x is like this. It's got to be below it. Now, it could be equal to it, but I'm making a comparison now. The comparison is f of x is greater than or equal to g of x is greater than 0 on the interval from a out to infinity. All right. I read that, understand it. So here's the part where it gets a little bit creepy for students, is understand what they're saying over here. Right. We understand these two things over here. Right. Number one, number two. All right. Let's read it. All right. As I'm reading, I want to make sure I'm understanding. I'm looking at this picture up here. I'm looking at that. All right. What does this one say? So it says over here, if we do a to infinity, f of x dx, and it's convergent, what am I saying? It's a finite number. Well, if that's a finite number, I hope you can agree that g of x is below that. It would also be a finite number smaller than that one. That's all we're saying. Now, here's what we're saying over here. If the g of x is divergent, what are we saying? It's blowing up. Right? The area under that thing is much bigger than any finite number. It's infinite. Well, if that's the case, f of x got to be bigger than that, and that's divergent. All right. So the bottom line is, someone says, well, gee, how could I find a comparison? Well, we try to keep it really simple. And what we do is we try to keep it really, really simple by, it says, useful note is often the following integral is used for comparison. So they're saying over here, this one here is going to be a useful integral for comparison, right? It's useful. So some of that, that's useful. What do I know about that? Well, we know some things about it. And what I'm going to say, it's going to be really easy to show. You may want to remember at this point. We'll kind of show that at some point. But we can show the integral is convergent for p greater than 1. And it's divergent for p less than or equal to 1. This is easy to show. But right now, let's just accept it. So what I'm going to say over here is that I want to make a comparison, but I don't know what comparison to make. But I'm looking at this guy over here. Let me write this down for you. And this is always tough for me, but let me write this down for you. It's going to be 1. Whoops, I don't mean to do that. I'm looking at the integrand. I did it again. I'm looking at the integrand. Wow, I'm really doing a lot of things again and again and again. I'm looking at the integrand. And I'm wondering, who to compare it to. And I'm saying it's got to be that 1 over x to the p. Well, I'm going to pick x to be, I'm sorry, I'm going to pick p to be 1. Sorry about that. I'm going to pick the p to be 1. All right, I'm going to erase the 1 now. And what do I know about this one over here? I know this integral here. I'll write this down for you. I know this 1 over x dx, 1 to infinity, is divergent. That's really easy to show, by the way. All right. What do I know about the other guy? And looking at it, I'm going to say looking at it, by the way, this is on that interval, it's definitely greater than 0. Put this over here. I know this is true. Now, so how do you know that's true? Let's go through it. So the bottoms are equal. I know that much. But look at this. This is 1 plus some finite number. It's certainly going to be bigger than 1. So what do I know? I know that this is divergent. So if this is divergent, this one is also divergent. It's larger. So this is also divergent. All right, let's look at the key. First thing you do, get a comparison going. That's true for all x greater than 0. If it's not, find some finite number that's above the 0 where it's going to be true. We know this is divergent. So if that's divergent, this wouldn't be divergent. How do we do that? By comparison theory. Comparison theorem often involves thinking, though. All right. Let me just see if there's anything else I have to say. And no, I just added some blank pages over there. I think we're done. We're going to go do examples now. And I'm hoping that you're going to give this a little bit of thought in the study department. All right. So let me stop the share. And give me a second here.